Hi, my name is Sudeep Pasricha, and I'm the director of the Embedded High Performance and Intelligent Computing Lab at CSU. In this video, I will give you a brief overview of some of the interesting research that is ongoing in our EPIC lab. So if you think about computing platforms at any scale today, be it smartphones or high-end supercomputers, they are all struggling to meet the demands of high-performance applications from the big data and deep learning realms. The platforms today are becoming more and more energy and power hungry and have higher temperatures. They're also more susceptible to faults and failures. They're having a hard time meeting real-time performance constraints, which is a big challenge in safety-critical applications, such as self-driving cars. And we also have to worry about security, not just software security, but also security challenges due to the increasing prevalence of hardware Trojans. To address all of these challenges, in my research lab, we aim to design novel software algorithms, hardware architectures, and hardware-software co-design techniques for energy-efficient, fault-tolerant, real-time, and secure computing. Our research targets computing platforms at multiple scales, from small system-on-chip designs up to larger embedded Internet of Things and cyber-physical systems, and then all the way up to large data centers and supercomputers. In the area of many-core system-on-chip design, it has become quite apparent that the biggest challenges have to do with data movement and data storage. So to overcome the data movement challenge, we have been designing new types of network architectures and protocols for CPUs and GPUs, including architectures that are more resilient to security attacks, new types of routing algorithms that are resilient to faults in 2D and 3D networks, and entirely new classes of network architectures that utilize photonics at the chip scale, providing much higher bandwidths and much lower latencies than electrical NUCs. We are also designing new deep learning accelerators with silicon photonics, where not only do we communicate at light speeds in the photonic realm, but we also perform computations such as matrix vector multiplications in the photonics realm to significantly improve upon deep learning accelerators that are out there today. To overcome the data storage challenge, we've been designing new types of memory architectures and protocols for CPUs and GPUs. For example, we've designed new 3D DRAM architectures that outperform other DRAM architectures. We've also designed a completely new class of main memory architectures using phase change non-volatile memory. We have also been developing sophisticated software-based resource managers for emerging CPUs and processing and memory platforms, where these managers intelligently map incoming applications onto the hardware platform while also tuning the platform to meet reliability, security, energy, and real-time goals. We've also been addressing many of these computing platform challenges at a higher embedded and IoT system level. For instance, we've done a lot of work in designing AI-inspired software managers for mobile devices. For example, reinforcement learning-based frameworks that perform mobile to cloud offloading in a sort of opportunistic manner to save energy, and new middleware frameworks that sit between apps and operating systems use machine learning techniques to reduce the energy overheads of executing different types of apps. We've also been developing new deep learning techniques for the domain of indoor navigation with smartphones. The challenges here are to train and deploy lightweight deep learning frameworks that still have high accuracy, but yet they can have very low inference time to perform real-time navigation. We have also been designing and deploying new types of deep learning algorithms for autonomous vehicle design. We've actually deployed many of these algorithms on resource-constrained embedded boards inside real vehicles. We've also recently been working a lot on enabling security in these connected and autonomous vehicles using machine learning techniques. Lastly, in the realm of data center computing, we have developed new types of software managers for energy efficient operation of data centers. More recently, we've also been looking at how to utilize geo-distributed data centers and how we can distribute workload intelligently across those different data centers to save on energy costs. We have also been designing new types of software mechanisms to enable fault tolerance for very large scale and complex exaflop supercomputer. Okay, to wrap up, if any of these research areas interest you, please feel free to contact me via email. I'm always looking for good master's, theses, and PhD students. And you may also be interested in some of the courses that I teach. Details of these can be found on my website as well. Thank you for watching and have a great day.